When you interact with a standard large language model, you are essentially talking to a highly sophisticated text calculator. It predicts the next word or sentence by analyzing patterns in language. But no matter how smart its answers feel, it is fundamentally blind to the physical world. To address this blindness, early AI systems used a technique called feature-level fusion. This approach bolts a separate vision encoder onto an existing text-based model to handle visual data. This vision model extracts features from an image and creates a numerical summary of what it sees. It then hands that compressed summary over to the text model to process alongside your prompt. The fatal flaw here is information loss. Because the text model only sees the summary, not the raw signal, it often misses critical micro details, like a tiny error icon in the corner of a screenshot, that were compressed away during the transfer. This architecture forces the system to compress the image before it even knows what question you're asking, which inherently limits how the AI perceives its environment. Modern systems solve this using native multimodality. Instead of keeping data types separate, they translate both text and images into a single, shared, high-dimensional mathematical space. Through tokenization, an image is chopped into tiny pixel patches, embedding each into that mathematical landscape as specific coordinates. Representing the same concept, the word cat and a visual patch of a cat's face will physically cluster together in the same sector. Translating words and visuals into a single mathematical language removes the need for separate models, eliminating the risk of translation errors. This shared space can also handle the dimension of time. Native multimodal systems don't just process video as a flat series of 2D photographs. Instead, they use spatio-temporal patches. These are 3D cubes of information created by extruding a pixel patch backward through time, capturing the motion of an object across a short window of video frames. This means the physical motion is mathematically baked directly into the token. The AI doesn't have to guess if an object is moving by comparing two different images. It sees the movement within the data itself. The ultimate benefit of this unified space is simultaneous attention. It allows the model to look at your text prompt and the visual tokens at the exact same time. Because the AI reasons about the user's question and the visual data concurrently, it knows exactly where to direct its focus within an image, solving the perception problems of older models. This coordinate system also works in reverse. Because the model maps different modalities to the same mathematical points, it can navigate from coordinates back into any token type, enabling any-to-any generation. By combining any input of text, image, or audio, the system can output entirely new cross-sensory results. It can navigate to a point in space using a text prompt and then read out a coherent video sequence based on the tokens it finds there. The AI can now translate information across different senses by navigating through this unified vector space. Treecapital's Anven 1.1 integration models apply this universal space to enterprise workflows with a specific architectural focus on visual reasoning. This late fusion architecture uses cross-attention modules that allow text tokens and encoded image tokens to feed into the same central processing core simultaneously. For developers, this architecture is triggered by placing the specific @image token immediately before the text query. This precise sequence activates the cross-attention mask, telling the model exactly which visual data to reason upon. In practice, this enables a model to handle complex visual logic, such as automated document auditing or circuit analysis, while running securely on-device at the enterprise edge. By replacing modular add-ons with a native late fusion architecture, Anven allows organizations to process multi-format data as a single unified cognitive layer.